Hello, I'm Andrew Montrose. This is Physics 2212, Lab 4, all about circuitry. The purpose of this lab is going to predict and model the behavior of circuits and how the currents and potential differences are affected by the components such as capacitors and resistors. You see a few images I have on screen. A few of these concepts will in fact be important. First, you have Kirchhoff's rules, that image in the middle. This the loop and node law. Essentially, we're going to be saying that the current thing that it's essentially talking about how we can add the currents together to find the total current, essentially. It's a little bit more complicated than that, but we don't really have time to go all into it. Then you have Ohm's law, which relates voltage, current, and resistance together. You see that in this little triangle image on there, but for now we can also sum it up in the law. We have the equation. We have circuits in series and parallel, which kind of goes in line with Kirchhoff's rules, and RC circuits, which are time-dependent circuits with capacitors. Now then, the actual experiment. First we have the model and the prediction. We have a little image of the model, and essentially we'll be using a PHET simulator for it. I predict that these circuits will be, the I1 and I2 will be the same as seen in the diagram above. Yeah, they'll be the same. They should be about 0.02. Sorry, the image got cut off a little bit. So the assumption that we'll make is that the resistance of the wire and the ammeter will be negligible, and the initial conditions, well, the initial conditions will be a little different for each one, and I'll go more in detail to each of them as for each of the different experiments. But the important thing to note is that the additional conditions for that the system will be the circuit itself, while the surroundings will be everything else. So let's actually get started looking at these experiments. First thing, experiment 1, we see the presence of the two, we have the initial condition will be two 1.5 volt batteries leading to a total EMF of 3 volts. So we have two resistors in series with a resistance of 47 ohms and 100 ohms respectively, and 1 ammeter before the resistors and 1 ammeter after the resistors. You can see how the circuit was arranged. And now my prediction would be that the currents measured in each of the ammeters would be equivalent, and that they should be approximately 0.0204 ohms and amps. And you can see that I derived that from Ohm's law. And in practice, we see that it is 0.02 amps with a voltage reading of 3 volts at I2, which we can see in the diagram on the bottom. Now, the disparity is likely just rounding, and you'll see that as a common theme. Now, this is sort of a continuation of the experiment one, where essentially we just took the different voltages for the different segments of the circuit, and we essentially used that to graph it below. Now, for the graph at the very bottom, and you can see how the potential differences sort of changed throughout the actual circuit. Now, in the potential differences, we also said they shall be a net of 0. This is because in this thing, the potential difference is path independent, so it doesn't really matter what path we take. It will always be the potential difference will be constant, and thus we'll say delta V is 0, and we get that answer right here. Now, the resistor and the ammeter in parallel, their values would be 48 ohms and the 102 ohms. This is very simple. We just used Ohm's law to derive that. See it again, and yeah, it's pretty easy to figure that one out. It's once again rounding errors. And then you have the actual resistance of the wire ammeter would be 0, and the current one in ammeters in parallel is 0.06 amps, which makes a lot of sense because the resistances of each provided by the resistors is actually divided up between the 2 amps, but the current should also be the same throughout. Now, for experiment number 2, we're going to instead have the 9 volt battery connected to a light bulb and a 200 microfarad capacitor, and essentially we just looked at the discharge times. Like the discharge time for the 20 ohm was twice that of the 10 ohm, and that the charging, and as it was charging, the voltage would rise and the bulb would slowly dim, and when it was discharging, the voltage would drop and the current would, while the bulb also dims, the current will also inevitably end up at 0 both times. Experiment 3 is essentially where we created an RC circuit, where we have a 9 volt battery connected to a light bulb and capacitor, and we essentially just use the little RC formula that we see here, the L and delta V. We plotted them into a little graph, and we use the slope to determine the actual RC time, and then we use the theoretical time for it, and they're pretty similar. The reason for the disparity is, once again, more than likely just rounding errors, but yeah, it's rounding errors or just timing errors. You know, it's a human error. I was using a stopwatch, and I could have timed this slightly inaccurately, but the general fact that it is very closely aligned to it does indicate that there should be some high level of there should be at least be some high level of precision here, which is always great. Now then, What if we did this in the real world, the ammeter would actually have some resistance. It's just due to the inert material properties of the ammeter, and the wire would also have some actual resistance. This would actually cause a lot of the times to be slower, and that actually translates over to the next question of if we used a real battery and all, and if this was in the real world, the charging and discharging times would actually be a little bit slower. Now, in an ideal thing, without no any resistors, it would actually be only 0.3 seconds for the capacitor to charge. Well, thank you, and have a great day.